Howdy, y'all. Dave Kennedy here. I'm here at the request of Katarina Yaret. She's our Vice President of Education, and she's asked me to produce a video where I could share my thoughts basically on any topic that I wanted to with our young professional colleagues. So this is the result. So I'd like to answer the question in about 30 slides. Can the Archie model be derived from first principles? So I don't know how expert you are in what Archie did. Most people are not very expert in what Archie did, but they learn about Archie from folklore, that is from other people, rather than reading Archie's paper. So it's always good to read the paper. At any rate, Archie did not derive his model, or build his model based on first principles, but rather it was purely empirical. And nobody even asked the question from 1942 when his publication appeared until 1978 when Ted Madden at MIT and publishing in geophysics sort of asked the question. Fractals were a new thing at the time, and self-similar models and that sort of thing. Anyway, Ted tried to derive Archie's equation from first principles with no success. And Pabrita Sen at Schlumberger et al. Even claimed to have done it in 1981, but his model was based on a effective medium model. And effective medium models are not what you would call first principles. And since that time, there have been many attempts, and nobody has come up with a satisfactory solution. Except, well, maybe David Herrick and myself have. So let me show you what I'm talking about. So the answer is going to be yes, but if you want to see how, you've got to keep watching. So we begin with a review of Archie. In his 1942 paper, Archie defines the formation resistivity index, formation resistivity factor, using this equation. So this is equation 1 in Archie's 1942 paper, and it says that the bulk resistivity of a rock is proportional to the resistivity of the brine in the rock, the constant of proportionality here being the formation resistivity factor. As a definition, it would have been more clear had it been defined as this ratio, the ratio of the resistivity of the bulk rock to the resistivity of the brine in the rock. So as you change the resistivity of the brine in the rock, then the bulk resistivity of the rock also changes such that the ratio is this constant formation resistivity factor. Archie went on to develop this equation that bulk resistivity of the rock is equal to the resistivity of the brine in the rock multiplied by 1 over the porosity raised to a power m. And this relationship was basically based on this data set. So this is the porosity formation resistivity data in the Nacatoch sandstone, published in Archie's paper in 1942 as a graph. There are no tabulated values. You had to hand digitize the values, but there they are, carefully hand digitized. So you can see that there is 1 decade of porosity here from 0.1 to 1, and there are 2 decades of formation resistivity factor. And if you let your eye follow the data trend, it projects down to about formation resistivity factor of 1 at a porosity of 100%. So we have 1 decade of porosity, 2 decades of formation resistivity factor. That means the slope of this line is 2. actually minus 2, except Archie has put a minus explicitly in his formula. And so m is just a number about equal to 2. So there is no physics in the Archie paper. There is no discussion of curve fitting. This is all there is. Now let's take 3 or 4 slides here to put you in the picture of, well, you'll need some mathematics if we're going to derive from first principles. So let me give you the mathematics that you'll need. It won't take long. So you would recall from high school algebra the formula for a quadratic function. So this is the y value is equal to a constant a times the x value squared plus a constant b times x plus a constant c. And this describes this parabola. So here is the parabola described by the equation, and the details of the parabola depend upon the values of a and b and c. Where the parabola crosses the x-axis, y is equal to 0, and so that gives you this equation, and the solution to this equation is where the 2 points where y is equal to 0. So these two x's, and I'm not going to discuss how you solve this equation. The method used is completing the square, and you can find it in your algebra book or maybe online, but the result is a well-known formula for the solution of a quadratic equation. 2 solutions actually, that's the plus and the minus, gives the 2 solutions. And except in the case where the parabola touches the x-axis only at one point. There's still 2 solutions, but they're both equal. So this is a degenerate parabola, and I bring this up because it makes it a convenient way to introduce the calculus that you need to follow these derivations. Now, it's very simple calculus, so if you've had calculus, you may remember this. And if you haven't had calculus, you should be able to follow it. It's only 2 slides. And this is a review of differentiation, and the differentiation that we will do is on this quadratic function that we just discussed. Well, differentiation, what does it mean? Well, let me go back. Let us write this in a more general form so that the independent variable shows up in each term of the formula. Not only does it show up in each term, it shows up with an exponent in each term. So this is the same formula written as explicit function of x to the power 1 and x to the power 0. Well, x to the power 1 is just x. X to the power 0 is just 1. So this is the same formula, but we want now to introduce a general term. So this is our general term. It's a coefficient, not necessarily that a, but it could be that a or b or c or any coefficient of x to a power n. And we're going to ask, well, how do you differentiate that formula? So our notation is d dx. d dx is an operator. That's what we call it. And the operator tells you what to do to this quantity in the parentheses. That's the operand. And what the operator for this polynomial, it's not a polynomial, but it's a term in a polynomial expansion, tells you to take the exponent and move it down in front of the a, and then subtract 1 from the exponent. So the formula would look like this. So here is n brought down in front of the a, and 1 subtracted from the exponent n. So that's what this operator is telling you to do. This is the operation is called differentiation, or taking a derivative, and the result is called the derivative. And so how it works for the first term in the quadratic, so we're going to apply it to each of the terms one by one, step by step, is that since the exponent is 2, 2 comes down, we subtract 1 from the exponent, and now let's just simplify this formula. So 2 minus 1 is 1, but x to the power 1 is just x. So the derivative of ax squared is 2ax. And we now apply this formula to the second term in the quadratic. Well, we're going to bring down this exponent, which is 1. So we bring down the 1, then we subtract 1 from the exponent. So 1 minus 1, and then we simplify the term. Well, it's b x to the power 0, but x to the power 0 is equal to 1. Any number to the power 0 is equal to 1, as you know. So we can just write b. So the derivative of bx is b. And finally, we have c written as c to the x to the power 0, and we apply our operator, and the operator tells us what to do. So we're going to bring down the 0 in front of the c, and we'll subtract 1 from the exponent, which was 0. So we get 0 times c, x to the minus 1. Well, 0 times anything is 0, so the derivative of this, and this is a constant, so the derivative of this constant is 0. So we see the derivative of y is equal to ax squared plus bx plus c is equal to 2ax plus b plus 0, so 2ax plus b. So that's the review of differentiation. And this is the review of integration. And for our trial function, we'll use ax to the power n again. And so here's the symbol for integration. Here's the argument or the integrand, and we're going to integrate with respect to x. And the formula for the result is given by, you take the exponent and raise it by 1 integer. And you divide the coefficient by the exponent plus 1 integer. So that's how you do it. So the integral sign is another operator operating on this function, and this is the rule that you apply to get the answer. So let's apply this to ax to the power 1. So that's just applying it to ax. Well, it means we're going to add 1 to the exponent, and that'll give us 2, and then we divide the coefficient by that number 2. So the result will be, after simplification, a over 2 multiplied by x squared. See that? Now we'll apply it to bx to the power 0. So we're just going to apply the recipe. So we bring down the, or rather we increase the exponent by 1, and then we bring down the result and divide this coefficient by the result. So it's b divided by 1 multiplied by x to the power 1, or bx. Now it turns out you can't really apply this formula to the special case of nothing. So you can't just integrate, let's say, there is no indefinite integral for nothing. But the so we write c to the power x of 0, well, or x to the power 0, well, that's 1, so that's c. And I'm not going to discuss this. You can look that up in the calculus book. That's beyond the scope of what we're doing. But I would say that when you look it up, you would find that a definite integral can be made that gives you, when you integrate nothing, that is just the integral of dx, integrated from 0 to c, the result is x evaluated at c at 0, which is c minus 0, which is c. But enough said about that. That completes our review of calculus. So now you have enough review to be able to follow the rest of this presentation, and this is slide 10, so there are only 20 slides to go, and we cover two topics. So this is a repeat of what Archie did. And now what we want to do to modify what Archie did is we want to ask the question in terms of conductivity. So sigma is a reciprocal of R, resistivity. Sigma is conductivity, so sigma naught is 1 over R naught, and sigma W is 1 over RW. And we want to ask the question, what kind of function of porosity is this? And what we're really asking is, for a change in porosity, let's call it delta phi, what is the change in the ratio of, so we're going to call this formation conductivity factor, which is what it is, or we could call it normalized conductivity. So what is the change in normalized conductivity in response to a change in conductivity? So that's the question that we ask for finite quantities, finite but small, delta phi and delta normalized conductivity. Well, these deltas, as these quantities get smaller and smaller, become our operator d phi, operating upon the normalized conductivity. So we're going to ask, well, gee, what does that look like? Here's a differential equation. It's going to tell us the slope of the function that we're looking for, and then if we integrate the function, then we will have the result we're looking for. That is, what do we put for the question mark? So that's where we're going with this. And we're going to need some observations in order to proceed, and we use Archie's Nacatoch sandstone again as our observation. We plot linear porosity versus linear formation conductivity factor, or normalized conductivity is another name for that. And we want to note the shape of the trend suggested by the data. So does the shape suggest a constant? So a constant would be a line across the x-axis, or above the x-axis at a constant value. So no, this data does not suggest a constant. So does this data suggest a line? Well, yeah, maybe you could say it kind of suggests a line, but what else could it suggest? Doesn't it appear to have a curvature to it in this direction, as if it is going to level out? The trend is going to level out down here somewhere. So another possible function is something like a quadratic. And then you could ask, do you see any other higher order trends in here? For example, if it were a cubic trend, why you would expect to see 3 zero crossings. It would go down here, come back 2, go back 3, 0 crossings. So we don't really see any indication of anything like that going on here. So that's what we want to note. We don't see that this data is a constant. We don't really see that it's a straight line, but it could be a quadratic. So now we want to do an exhaustive search of the solution space. So here is our the slope of the line that we're looking for, and we're going to say the slope of the line could be 0. It could be a constant. We'll call it alpha. It could be a linear function of porosity. We'll call it alpha phi plus beta. It could be a quadratic function of porosity. So we'll call it alpha phi squared plus beta phi plus gamma. Or it could be a higher order polynomial. So we'll just call that et cetera, and you know what et cetera means. It would be alpha phi cubed plus beta phi squared plus gamma phi plus delta, and so forth. So we're going to examine these one at a time. So we begin with case 1. Case 1 is our case where the derivative is equal to 0. Well, if the derivative is equal to 0, then the function is equal to a constant. Well, that's not observed. So case 1 is not what we're looking for. So now we look at case 2. So the derivative of normalized conductivity with respect to porosity could be a constant. Well, if it were, then the normalized conductivity would equal this linear function, and that is not what we observed. So case 3, our next case, is the derivative of the normalized conductivity with respect to porosity is equal to a linear function of conductivity, that is a line. So let's integrate that, and the solution of that differential equation is alpha over 2 phi squared plus beta phi. So that, in fact, is what is observed. We're observing something that looks like a quadratic. That is, it looks like the right limb of a parabola. So we're going to say that that's observed. In case 4 was for this higher order quadratic. It's the derivative of the normalized conductivity with respect to porosity. A quadratic function is the derivative. Well, let's integrate that. And the integral would then be this cubic function, this polynomial of order 3. And we don't see that. So that's not observed. And if we went to higher order polynomials, they would just oscillate more than the cubic polynomial. So we don't feel the need to go any higher than the cubic in our search of the solution space. So let's say that case 3 is what we've observed. What about boundary conditions? So when you solve a differential equation, you have to apply conditions at the boundaries if it's a spatial equation, or initial conditions if it's a temporal equation. So this is more like a spatial equation that we have. So our differential equation that we solved was the derivative of normalized conductivity with respect to porosity was this linear function, and the solution of the differential equation for normalized conductivity is this quadratic function. Can we evaluate the constants? And the answer is yeah, we can, because we know that when porosity is 100%, that this ratio will be 1. So we can write 1 is equal to alpha over 2 plus beta. And we'll talk about the other boundary condition in a moment. But here's the one that we just talked about, that evaluated at porosity equal to 1, then our function is alpha over 2 plus beta, and that is equal to 1. Now, when we evaluate the function at the left side of the interval, that is at phi equals 0, well, in order to do this, we want to do a trick, because there are two solutions here. And so we factor out a factor of porosity, phi, leaving behind alpha 2 times phi plus beta. And then we're going to plug in for 0 the value of porosity at 0. So that's 0 here and 0 here. So this term is equal to 0, or in other words, beta is equal to 0. So we've evaluated our constants that alpha over 2 plus beta is 1, but beta is 0, so alpha over 2 is 1. So now the constants are evaluated. So we write our solution to the differential equation as, well, these are the boundary conditions. And so our solution to the differential equation is the normalized conductivity is equal to the porosity squared. So because alpha over 2 is equal to 1 and beta is equal to 0. So if we unpack this normalized conductivity, then we get sigma naught is equal to water conductivity sigma W times the porosity squared. And in terms of Archie's model, if we reciprocate the conductivity of the rock and the conductivity of the brine and the phi squared, then the result is R naught is equal to RW, phi to the minus 2. So the claim here is that we have just derived Archie's law by an exhaustive search of the solution space. So still looking at the boundary conditions, we want to go back to this form where we factor out a phi. And here we want to, for purposes that will become apparent, instead of taking alpha exactly equal to 2, take alpha approximately equal to 2. So that means alpha over 2 is approximately equal to 1, but not exactly equal to 1. And we're going to define that as A naught, which is a constant almost but not quite equal to 1. And we're going to define a constant B naught is equal to beta. And it's a constant almost but not quite equal to 0. And then we write our solution that the normalized conductivity is equal to the porosity times the quantity A naught phi plus B naught. And we call the quantity A naught phi plus B naught E naught. And this is known as a geometrical factor. So finally, we unpack this equation and we write the conductivity of the bulk rock is proportional to the conductivity of the brine in the rock, proportional to the amount of brine in the rock, and proportional to some kind of geometrical factor. We also note that the geometrical factor is approximately equal to the porosity. So what's the bottom line of all of this? So here we're at equation 21. Or page 21. Well, here's our function, and the bottom line is this thing, which is called, as the name, a triple product theorem. So here's the question. Can the Archie model be derived from first principles? Well, is an exhaustive search a first principle? So to tell you the truth, I don't know. Maybe not. So keep watching. Here's 3 first principles. Bulk conductivity is proportional to, first principle, the conductivity of the interstitial brine. Bulk conductivity is proportional to, a second factor, the amount of the interstitial brine. And bulk conductivity is proportional to the geometry of the interstitial brine. And we can translate these English words into equations. That is, the conductivity of the bulk rock is proportional to the conductivity of the brine. The conductivity of the bulk rock is proportional to the fractional volume of voids, or the porosity. And the conductivity of the bulk rock is proportional to a geometrical factor that we call E sub naught. So if we put all of these proportionalities together, then the conductivity of the bulk rock should be equal to the product of the conductivity of the water, the conductivity, or the amount of brine, and the geometry of the brine. Well, this is the triple product theorem. And you don't have to believe it unless somebody proves it to you. So that's what I intend to do now. So the proof of the triple product theorem, looking at the first proposition that the bulk conductivity of the rock is proportional to the conductivity of the brine, that's taken as self-evident and stated without proof. So I don't try to prove that. Notice that basically this is the same thing that Archie has written when he writes R naught is equal to FRW. This is, which he also states without proof. Now, the conductivity of the bulk rock being proportional to the first power of porosity for constant brine geometry. So what do we mean by that? Well, here's a model core plug, and we've put all of the porosity into a single tube. And it's a sinuous tube, so the tube is longer than the core plug length. And the ratio of the volume of the tube to the volume of the core plug is the porosity. And we call it the porosity of the channel because we're going to call that a channel. And for convenience, we call the porosity of the plug with the single channel sigma sub 1 because it has one channel. Now suppose we add another channel exactly like the first channel. So it has the same shape, it has the same amount of void space. The only difference, well, there is no difference. There's just two of them in parallel. Well, there's the total porosity then is the porosity of two channels. So two channels, and the conductivity is proportional to twice the conductivity of one channel from the two channels. And it doesn't really matter what the complication of the shape of the channel is, as long as the channels have the same shape as they increase, then this proportionality holds. And so for n channels, then the total porosity would be n times the porosity of one channel, and so the conductivity of the bulk rock would be proportional to the total porosity, as we asserted. Remember, that's for constant brine geometry, and people say, yeah, well, this is a toy rock, this is a cartoon proof, it doesn't prove anything. So I give you one more proof of the same proposition that the bulk conductivity of the rock is proportional to the porosity. So if you imagine 8 quarter cylinders, and well, imagine 2 quarter cylinders. One of them has 0 porosity, and the other has porosity of 30%. And these are cut from rocks. So the pore system within the quarter cylinders are rock-like pore systems. And then we duplicate each of these quarter cylinders so that we can make full volume core plugs out of every possible combination of the cylinders. So here are 4 0 porosity cylinders. Here are 3 0 porosity cylinders and 1 30% porosity cylinder, and so forth until we're all 30% porosity cylinders. And we ask, what is the conductivity as the porosity scales from 0 to 7.5 to 15 to 22.5 to 30%. And the claim is that it is obvious that the porosity, that the conductivity scales with the porosity even using a rock-like pore system. So that just confirms that for constant brine geometry, that the bulk conductivity of the rock is proportional to the first power of the porosity. Now we're going to look at the brine geometrical distribution. So this represents a core plug with a distributed brine in the pore system, and we want to examine what happens if we take all of that porosity and put it into a single through-going tube, and we use the remainder of the material here, the quartz, to make the walls of the tube. And so this tube is as efficient a conductor as you could possibly get, except we interrupt the end-to-end conductivity with a cut. And this cut is shown bigger than it needs to be just for purposes of clarity. And in that case, the bulk porosity of this core plug, model core plug, will be 0. So the minimum conductivity is going to be 0. On the other hand, if we don't make the cut and we have a continuous tube from end to end in our model core plug, then we have a maximum of conductivity, and that maximum of conductivity is equal to the conductivity of the brine in this tube multiplied by the porosity of the bulk medium, which is the ratio of areas of these two tubes. And so we've got that the observed bulk porosity is greater than the minimum and less than some maximum. And so we can write our triple product theorem as bulk conductivity of the rock is the product of the conductivity of the brine, the amount of the brine, and this geometrical factor, where the geometrical factor is a number between 0 and 1. And the question is, well, okay, but how do you get the geometrical factor? And the answer to that is, if we solve this equation, if we solve our triple product theorem for the geometrical factor, then all of the quantities on the right side, so bulk rock conductivity, brine conductivity, and amount of brine or porosity, all of these are directly measurable. So if we have an ensemble of core plugs, then for each core plug we can calculate E naught, because we have all of that. And then let's take a look at what happens if we take Archie's data and we calculate E naught for the Archie data and plot it as a function of porosity. So here is the data point, here's the trend through the data. And if we fit the trend with a line, so this is E naught is going to be equal to some function of porosity. If it's a linear function, then we will have a coefficient of porosity, 0.921. This would be alpha, approximately equal to 1. And an intercept of 0.0264, this would be beta, approximately equal to 0. And we would note that at every point along the line, that the geometrical factor is approximately equal to the porosity. Say, for example, here's 0.4 porosity, and here is 0.4 E naught. So this little difference here in these regions is the difference. And I would just point out that these three outliers, and who knows what these are because they don't look like they're part of the trend here. If you leave these out, and I haven't done this for this presentation, but if you leave them out, you can take my word for it that this number is much closer to 1 and this number is much closer to 0. So here is our function that we get to relate or to correlate the geometrical factor to the porosity. So E naught is equal to A naught phi plus B naught. So what's our bottom line here? Well, we claim we have proved the triple product theorem. So here was the triple product theorem. Here it is written with E naught as a function of porosity. And QED, that is the end of this presentation, where we claim to have shown you two different ways to derive the Archie equation from first principles or something like them. So this is the same result as the exhaustive search, as it should be if both of these are correct. And then the caveat is, now this only works for Archie rocks. So this is a model for Archie rocks, the same as Archie's model is a model for Archie's rocks. So here's our model. And to put it in Archie terms, we drop the B naught almost equal to 0 and we keep the A naught. Except now, if we put it in Archie's terms, we let this coefficient be 1, but we change the exponent to a variable. So instead of our variable being the coefficient and not the exponent, we set the exponent equal to the variable, the coefficient equal to 1, and make the exponent variable. So this is Archie's law written in terms of, or Archie's relationship written, Archie's model written in terms of conductivity. Here it is with reciprocated quantities plugged in, and here it is solved for R naught. So this is Archie's model as he would have written it. Archie rocks are water wet. They have only interstitial porosity, and brine is the only conducting phase. So any rocks that are oil wet or have secondary porosity of any kind or have conducting minerals such as clay of any kind are not Archie rocks, and you can't apply these formulas to those kind of rocks. If you wanted to read some more about this, there's a recent paper by David Kennedy and Freddie Garcia, Introduction to Resistivity Principles for Formation Evaluation, a tutorial primer. And this paper has 2 additional proofs of the triple product theorem, as well as one that we just proved. So in formation evaluation science, we leave you with quad erat demonstrandum, or QED. QED Petrophysics aims to take the empiricism out of our science of formation evaluation as much as possible. And that will be it. See you next time.